La 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 la. Alright, this is Dr. Smith, and I am going to try to explain or summarize for you how Ampere's law works. So this statement here is the most basic statement of Ampere's law, and it's kind of scary because it's got an integral in it, and it's a multivariable integral, so it's an integral of this dot product, and so you wonder what the hell does that mean. So that's the left-hand side, and what you're doing is you're integrating the magnetic field all the way around a closed curve, some kind of boundary, and then there's this surface that's surrounded by the curve. So everything inside the curve is a surface. And the right-hand side of the equation says that when you do that whole integral, that what you get out is equal to mu naught, the universal constant for magnetism, times the total enclosed current going through the surface. Okay? Now, this seems a little scary, but it's not very hard. So, let's say first of all, I think it's pretty clear that what the right-hand side means, is not hard to figure out. You have to find the total current that goes through the surface outlined by this curve and multiply by mu naught. That's not hard. The hard part is understanding what this integral means. So let me try to sort of explain it in a series of discrete steps. So to go around this closed curve, which is what you're doing in the integral, and by the way, some people put a circle on the, wow, that's horrible. So some people put a circle on the integral sign. That's a little better. Still kind of ugly. The idea is, as you're going around this curve, you break it up into a set of steps. And like that could be one step. That could be another step. This could be another step, etc. And each of these steps, I'm going to call delta S with a new number on it. So this is going to be delta S1. This is going to be delta S2. This is going to be delta S3. Now, this looks like a series of sort of big steps. And the idea really is when you're integrating, you actually do very small steps. In fact, so small that you might as well be actually walking along all the curves. So I'm just sort of, showing you like an exaggeration of the size, a schematic to try to get you understanding what's going on. But what you do is for each of these steps, for example, for this delta S1 step, you find out what the magnetic field is in the area that you traverse with the step. Let's do lavender. And let's say right here, the magnetic field is B1. And then over here, the magnetic field is B2. When you're taking step 2 in this area here, the magnetic field is B2. When you're taking step S3, the magnetic field is B3, and so on and so forth. Where does this get you? So eventually you take enough steps to go all the way around. Okay, so eventually you get up to the point where you've gone doop-doop-doop-doop, and you've walked around this whole curve, which looks like, I don't know, looks like Australia, I guess. So you've walked all the way around Australia, and you've gotten back to the beginning. And what you do is you take for each of these steps, you find the dot product of B for that step. So for example, down here we're going to say B1 and delta S1. Okay, so that's the dot product for the first step, and you add up the dot products for each of the steps. B2 dot delta S2. Okay, and so on and so forth, dot, 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 until you get up to the last one, and I'm just going to call that B subscript n, where n is the total number of steps you took. Okay? Yeah, that's not 2, sorry. Should be delta Sn. There we go. And so, when you add all those up for small enough delta S's, really infinitely small, but, small enough for small enough for government work is fine, then what you'll get is that's the value of this integral. Okay? And that's what's equal to mu naught times I enclosed. And it's more understandable, I think, when you actually see an example. So, whoops, I'm going to launch straight into the first example I have, which is the field around a wire. So let me move forward here. Let's see. Yes. Okay. So let's take the field around a long straight wire. So here, this circle with a dot through it is a wire with some current I, long, straight wire. By long, we mean infinitely long, effectively. And we want to find the field, the magnetic field, at a distance r from the wire. Okay, so here we go. Right there. Yeah, that'll be good. And this distance is r. We want to find the field at this point here. Okay, so easy enough. What we do here is we find a curve to apply Ampere's law to, and we call that an Amperian curve. This is similar to the idea of Gauss's law, where you pick a surface. Here we're just picking a curve, and we want to pick something that's nice and symmetric and easy to do the integral over. In this case, we just do a circle with a radius of little r. So the Amperian curve, and I'm just going to sort of write down the steps in the derivation, is a circle with radius r. Okay? So what do we know about the magnetic field in the circle? Well, for starters, we can look at symmetry, and the symmetry of the, let's go with orange. The symmetry of the problem suggests that at any point, no matter where we're looking at, the magnetic field will be the same, because we could just rotate this whole curve and everything and make any of these points into any other point. So they all have to have the same magnitude, at any given point on the circle. The magnetic field has to have the same magnitude. Sorry, I'm still getting over being sick. By symmetry, magnitude of the magnetic field is uniform on the circle. Okay, next thing is which way does the field point? It could point, that way. It could point tangent. It could point inward. It could point outward. Can we eliminate some of these? Well, we can say it's not going to go inward because magnetic field lines can't be created or destroyed. So if you had magnetic field lines going inward, then they'd have to be going inward at every point by symmetry, right? But then you would end up with magnetic field lines getting crowded here in the middle and nowhere for them to end. Magnetic field lines always form closed loops. And people have asked, well, can't they go in the z direction? So can't they go into or out of the page? They can't because, it's a good question. They can't because of the symmetry of the problem in the z direction. So we should be able to apply the same analysis everywhere along the wire. It's a long straight wire, effectively an infinitely long wire, right? And if our magnetic fields that curl inward here then went into the page or out of the page, we'd basically be sending them to another, another section of the problem, but we still wouldn't have any way to get rid of them. And it's not fair, I guess for lack of a better word, it's not fair to dump your magnetic field on some other section of the problem, because then you can't, it's like it's like if you and your friends were cleaning a section of a highway. Say you're like the one of these clubs or organizations or whatever that gets the Adopt a Highway program, and so you get like a kilometer of highway, and you and the other 99 members of your clubs, there's 100 of you, go out and each of you decides to take a 10-meter section of the highway and clean up the trash there. Well, suppose everyone just decides to kick their trash 1 meter, or not 1 meter, 10 meters down the road into someone else's zone. Then everybody kicks their trash into the next person's zone, but nobody ends up with less trash to clean up because they've still got the trash that some other jerk kicked into theirs. Except the people on the end, well, the person on the one end who didn't get it and kicked into his, but that's the point where that's sort of the exception that proves the rule, because that's the very end of your kilometer of the highway. And in fact, when we have this long straight wire, quote unquote long, what we mean is infinitely long. So there is nobody at the end of the highway or at the end of your kilometer who doesn't lose from this. So that eliminates the possibility of them going in, and I think you can understand that by the same logic, there's no possibility for these guys to go out either. So the magnetic field, you could say it's also by symmetry really, must be tangent to the circle. Or you could say, let's see, by the fact that there are no magnetic monopoles. So by the, let's see, what can we call it? You could say there are no magnetic monopoles. So no positive or negative magnetic charges. So no magnetic monopoles means that B must be tangent to the circle. Okay, so now we know that the magnetic field at any of these points has the same magnitude. It's always tangent to the circle. So let's look at what happens when we have our little delta S vector at any point on the circle, which I'm going to do in purple now. Say right here, our little delta S vector is going around the circle, and it's pointing the same direction as the B vector. If we go up to the top here, our delta S vector also points around the circle, and that means it goes in the same direction as B. So at any given point, let's do it in this color. At any given point, this B dot delta S vector, for any of them, okay, is really just the magnetic field magnitude times the magnitude of delta S for any delta S on the circle that's sufficiently small. Okay, so I mean, obviously if you took like from here to say here, you get this line that crosses like that, and it would, you know, where do you pick the magnetic field? But that's not really what we're talking about. We're talking about small delta S's and adding them all up. And so what you're going to get from this is, let me see where I can put this. What you're going to get for this is that the integral of B dot ds over the entire thing equals the magnitude of the magnetic field times the circumference of the circle. And what's the circumference of the circle? It's 2 pi r. Okay, so now going to this page and writing down Ampere's law, we get integral, I'm just going to write the whole thing again, integral B dot ds equals mu naught times I enclosed. This is Ampere's law here. So substituting in what we got on the last page, we got B times 2 pi r equals mu naught times, and then our current enclosed in the loop is just I, right? So looking at this loop, or this Amperian curve, Amperian loop, whatever you want to call it, the only current inside was I. This is the current coming straight out towards us. So here we go. So that just means that then we want to solve for the magnitude of the magnetic field. B equals mu naught times I over 2 pi r. And there you go. That's the formula for field around a wire. Okay, so that's how you can derive that. Field around long, straight wire. And in a moment, I will show you, if you want to watch the next video, I will show you how to do it for a solenoid and for a toroid.